Welcome to part 2 of the module on the benefits and limitations of patterns and frameworks. In part 1, we went through the benefits and limitations of patterns. In this part, we're going to continue our discussion focusing on the benefits and limitations of frameworks. There's a number of benefits of frameworks. One of the most important ones, which is a nice segue from our discussion of patterns, is that frameworks help to guide application developers through the steps that are necessary to ensure the successful creation and development of software by emphasizing design reuse. And invariably, this design reuse is captured and characterized in the form of patterns. For example, when we developed our implementation of real-time Corba, by that point, myself and my design team was very well versed in the patterns for building communication middleware. And so when we went to build our implementation, we used those patterns as a guide to help us address key common recurring themes, roles, relationships, interactions, and conventions that we learned from other domains and apply them into the domain of real-time communication middleware. But reuse of design is not enough, as we had talked about before in the last part of this module. Reuse of design is crucial, it's necessary, but it's not sufficient. And the reason, of course, is it takes too much work to re-implement those designs by hand. So one of the nice things that frameworks do is they go one step further and they provide a reusable collection of components that are integrated and work together to provide a reusable architecture and implementation for a family of related applications. So in other words, the frameworks actually take the patterns and other aspects of design and other insights, and they actually allow you to create working software that leverages prior investment, prior implementation work, prior optimization efforts, and so on, thereby helping to amortize the software development cost. So of course, when we went to build our real-time Corba middleware, we had the benefit not only of the patterns, but we also had the reification or the instantiation of those patterns in the ACE frameworks. And so many parts of our middleware was implemented using ACE, which provided some of the lower-level infrastructure components for event handling, concurrency, synchronization, service access and control, and so on. And that was one of the reasons why we were able to produce such a high-quality solution in such a short time that was so portable and so optimized, because we weren't starting from scratch. Another very important benefit of frameworks is the ability to reuse the validation and testing efforts. One of the things that makes it hard to build software, it's not hard to build software, it's hard to build software that's going to be correct, it's going to be portable, it's going to be portable to different operating environments, portable to different configurations of the operating systems, the network protocol stacks, and so on. And then making sure that you've shaken all the legs, all the errors out of the error legs, and gotten the problems out of the code. Well, needless to say, this is a very tedious and time-consuming set of quality assurance operations. And so one of the great things about frameworks is they help to amortize the QA activity, the quality assurance activity, the testing and the validation. And one of the things that we've done extensively in our work with frameworks is we've built automated regression test environments, such as the one that's shown here on this slide, where we run our software, middleware, frameworks on a whole variety of different test platforms with different operating systems, different compilers, different configurations, turning on threading, turning off threading, and so on and so forth. And then having the ability to automatically determine through testing which of our regression tests are working and which ones are failing at any given point in time. And of course, by displaying all of this information in a nice web-accessible dashboard-like manner, it's easy for the development team to track this, to make sure that if a problem occurs, it's quickly identified, quickly remediated, thereby allowing the end users of the software the benefit of all this automated or semi-automated regression testing. Once again, frameworks are invaluable if you build this kind of an infrastructure, because that amortizes those tedious and error-prone QA processes and the effort required to do them. There are, however, a number of limitations with frameworks, and we have to be front and center about this so people don't get fooled into thinking it's a magic panacea to solve all the problems of software development. One of the key challenges with developing and applying frameworks is that many application developers find it difficult to use them because they're not necessarily familiar with some of the object-oriented language features like inheritance and dynamic binding, or even in some cases parameterized types, templates. And they may also not be familiar with some of the patterns that the frameworks embody, which means that they've got an awful lot of complex surface area to try to navigate. Another key challenge here is that the way in which you build frameworks, which is a process called scope, commonality, and variability analysis, requires a great degree of design expertise and domain knowledge from the development team. And sometimes software developers, especially those who have a language-centric view of the world, may be very facile with C++ or Java, but they may not be familiar with the issues of multi-threading, or they may not be familiar with the issues of real-time processing, or dealing with partial failures, or causal ordering, or distributed deadlock, and so on. And a good framework is by very nature domain-specific, and that implies the people who build it have a great degree of knowledge of the domain. Another challenge with frameworks along these lines is that if you have the situation of trying to implement and apply a framework in a non-object-oriented language, things can get very complicated. Because a lot of the things you would take for granted in a language like Java or C# or Python or C++, in terms of abstractions like inheritance, dynamic binding, parameterization, and so on, are often missing or done in a very different way in non-object-oriented languages. So there's going to be a lot more code that you're going to have to write and learn, and the language itself won't always guide you as cleanly to make the right implementation and design choices, thereby making the results more complex. Here's just a very simple example of this. This isn't really a complicated framework. It's just an illustration of the use of the strategy pattern applied in the context of C for the standard C library function qsort, where you can strategize the way in which comparisons are done by passing in a pointer to a function. If we were programming this in STL or Java, it would be much easier to make this solution type safe, easier to understand, and so on, once you understood the patterns of STL or the patterns of generic programming. When we do it in C, it's a little bit lower level, it's a little bit more error prone, accidental complexity can rise up and bite you when you least expect it. So it's not that you can't implement and use frameworks written in non-object-oriented languages, it's just that the surface area is much more complex and there's a lot more dark corners and sharp edges you have to contend with. Let's say that you're not trying to build a framework, you're just trying to apply one. Well, there's some limitations and challenges here as well. It is often a non-trivial task to figure out how to evaluate some framework you're considering for use in terms of its applicability, in terms of its quality, in terms of its footprint, in terms of its cost, etc., for a particular domain. This takes a while. Sometimes people don't have funds to spend time doing the trade study analyses to figure out what's the right solution, even though inevitably there probably is one somewhere, either in a closed or open source manner that they could apply to solve their problem. And that takes time. Another potential problem or limitation with frameworks is that their use of so-called inversion of control can make debugging somewhat tricky. Inversion of control is one of the key driving characteristics of a framework. And what it typically implies, as we've talked about before, is registering some kind of function or object or component which gets called back by the framework when something interesting happens that the framework has detected. And that's typically the way that frameworks are organized by inversion of control. Rather than self-directed applications, they're driven by callbacks. Well, this is very powerful, but it also means that when something goes wrong and you're stepping through your code in a debugger, you'll often find long sequences of backtraces that you know little or nothing about and may not even have the source code to adequately debug because the framework was written by someone else and they own the main focus of control for most of the application. This takes a little getting used to. It's one reason why open source techniques can often be very appropriate because you can actually dig down if you need to and find out what's going on. It's also a good place to use common tools such as Valgrind that can be applied to detect memory corruption in your software. Sometimes you'll have a mistake in your code that won't manifest itself until the framework does something, and then it looks like it's the framework's fault, but it's really because the objects or the functions or the data have gotten corrupted somehow from some other application level mistake. This leads into one of the other limitations with frameworks. Even though I mentioned before that it's possible to do a lot of validation reuse, run regression test suites, be able to do various kinds of validation and verification in an automated way to amortize those costs. Sometimes, especially in a highly parameterized framework, it's very difficult to know that the framework is correct or not because it only manifests problems when you instantiate the framework components in particular ways. And if you don't account for those different variabilities in the test suites that you do, there could be latent bugs, latent defects lurking in your framework code for a long time that only manifest themselves when some unsuspecting application developer applies things in a way not anticipated by the testing team. This, of course, is just another variation on the old cliche that you can't test correctness into a program. Testing only finds the presence of bugs. It doesn't prove the absence of bugs. So this, of course, argues in favor of other techniques, model checking, static analysis, very thorough regression test suites based on automation, the use of continuous integration facilities like cruise control and other tools to automate the testing. It also argues in favor of the use of test-driven development methods where you write your regression tests ahead of time prior to writing the software. Many of these concepts are very popular in the agile world, but they apply in other methodologies as well. And another problem you often run into with frameworks is that performance can be degraded due to the very complex internal structures and many levels of indirection that are often baked into the framework. This is not inherent. There are many frameworks that have been highly optimized for a wide variety of demanding mission-critical domains, distributed real-time embedded systems, cyber-physical systems, and so on. But if you're not careful, especially if you use languages that don't really force you to think carefully about all the optimization considerations, you can end up with a fair amount of overhead. That's one reason why people sometimes are reluctant to use off-the-shelf frameworks, off-the-shelf middleware for these more mission-critical, real-time embedded systems, because they're afraid that the additional overhead will prevent them from being able to meet their end-to-end quality of service requirements. I've written a paper that you can take a look at this link that talks in great detail about the benefits and limitations of frameworks and provides pointers to other literature and other places you can find more information about this topic. So to summarize this particular discussion of frameworks, key insight, key advice: don't blindly apply frameworks, don't blindly apply patterns. The abstraction and indirection that they provide, which are good often, can sometimes lead to increased complexity, cost, confusion. One reason why it's so important to document your software frameworks using patterns. As a general rule of thumb, understanding patterns can be very effective to help learn how to better develop and apply frameworks. I've done this throughout my career. This is a synergistic process. As you build more frameworks, as you build more applications with frameworks, you'll understand patterns better, you'll discover new patterns. Those patterns can make you more effective at being able to develop new frameworks. A lot of the work that we've done over the years with ACE and the ACE orb or DAO has involved applying frameworks, learning the patterns, using the patterns and insights of patterns to improve and enhance and extend the frameworks. It's a nice control feedback loop. You can also view patterns as essentially abstract descriptions of frameworks that enable broad reuse of software architecture. Architecture has a number of different definitions. One common one is it's basically describing the key components and their interactions, their structure, and the control flow between the components. And patterns do a great job of being able to identify and justify why those interactions occur. Likewise, frameworks can be viewed as concrete realizations of patterns, or more likely, pattern languages that facilitate direct reuse of detailed design and code. So you can see why these two techniques work together so effectively. One gives you the abstraction reuse. The other gives you the implementation reuse. Apart, they certainly have benefits. Together, they're even more powerful. It's also important to remember that patterns and frameworks done right is even more challenging and complex than trying to do good object-oriented design. Good object-oriented design is something that takes years to master. Knowledge of patterns is crucial, but knowing how to discover and document common useful patterns and how to instantiate those patterns in the form of efficient, portable, extensible frameworks is even more difficult than doing designs. So it should be no surprise that this is something that takes study. One reason why hopefully you're watching this course, so you can learn also to navigate through the maze of complexity to become a much more effective developer.